this computer. Okay. So what I wanted to give you guys a heads up on was the written final exam. Now, people are falling out. Okay. No, I don't want, I just want to write my own. Let's see. We can see what you share here. I don't want, no, that was dumb. Isn't there like a classical whiteboard that just worked? You know what I'm going to do is I'm going to do something different, not that. I'm going to use a blank PowerPoint so then only I can write on it. And then y'all will be able to see that. Now I got to switch my share. Really happy that I'm recording all of this. Okay, so here we are. And I'll go ahead and say a decent job of watching the chat. So if you have questions, feel free to add them to that. I wanted to give you an overview of your written final exam. That exam will be 1 week from today. And it's typically 20 to 25 questions. And about half are multiple choice and half are short answer. When it comes to this exam, I typically, I'm not trying to torpedo anyone's grades or do anything like that. Some of the questions that I ask about, and one of the things that you should expect is I'll give you a Bradford line of best fit. Equation. And I'll give you a little details about, the experiment and what's the concentration of a sample. So you might have to worry about or think about a dilution factor there. So take that into consideration. Then I like to ask about names of enzymes that we've looked at, and then reactants of those enzymes. And then any sort of buffered solutions, and particular with respect to an enzyme. What's unique about the buffer that we use for our enzyme? And the answer to that is that it has a pH of approximately 12. Or sorry, 10, not 12. A fairly basic pH. Now, I want to bring this back up. The enzyme is lactate dehydrogenase. Lactate dehydrogenase. And I'm pronouncing that and writing that out because the name is significant. And I just want to contrast that. I'm not going to write this out so that I don't cause any confusion, but I'm going to contrast that with something like lactose dehydrogenase. Well, that would be lactate is one of our reactants, and a dehydrogenase is an oxidoreductase enzyme. So an oxidoreductase that acts on lactate as opposed to lactose dehydrogenase. Well, lactose is a sugar. And yeah, it's a dehydrogenase, or lactose dehydrogenase would be doing an oxidoreductase reaction, but that's not the specific reaction we're interested in. The reactants that we used NAD plus and lactate. And our products for this reaction were NADH plus pyruvate I think that it's important for you to be able to identify NAD plus and NADH based on which one is the oxidized and which one is the reduced form of this substance. So if you think about it as NAD plus versus NADH, well then NADH, let's think about this. How do we go from something that's neutral to something that's positively charged? Well, to go from something that's neutral to positively charged, we have lost an electron going from effectively 0 to +1. Because if you think about it as adding an electron plus E, you would get something that is negatively charged, adding it to something that's positively charged, that would get you to that neutral charge or that neutral electronic state. So what that means effectively is that NAD plus is your oxidized form, and NADH is your reduced form. So that's kind of our reaction that's taking place there. Our reactants, NAD plus lactate, buffer is pH of 10. NAD plus is getting reduced to form NADH. And if NAD plus is getting reduced, that means that lactate is getting oxidized, and vice versa. Now, whenever I ask about reactants and products, that's typically a place where I definitely leave some room for interpretation and leave open some space for different answer options, because truly this reaction is NAD plus lactate, and it goes in both directions to make NADH pyruvate. So you can definitely make a case that our enzyme, well, the reactants are NADH and pyruvate. Yeah, totally. The reactants are NAD plus and lactate. Yeah, totally. So I do leave open some flexibility for that, but I think that it's helpful to remember, what did we mix up? We made a master mix with NAD plus and lactate. And so our reactants, our perspective is these are our reactants. These are our products. Can the reaction go in the opposite direction? 100%. But think about what you actually did and how that relates to the question that's being asked. This was significant, and this is an enzyme that we can use because it gives us a metabolite that can be tracked by measuring absorbance at 340 nanometers. So by measuring our absorbance at 340 nanometers, we can use the Lambert-Beer law to calculate, to do some calculations on basically the appearance of that and the rate of our reaction. So if I ask you to do a calculation regarding the Lambert-Beer law, I would give you extinction coefficient and I would give you like details on the experiment. And what I mean by that is if I need you to go from molar per second to or I'll just say millimole per hour. These are not the exact same components of the calculation that we did, but I would give you, I think, the appropriate information. I would give you enough information to do this calculation. I'm just kind of putting this out here as a hypothetical, like I might give you, here's another enzyme that you track this metabolite, which has a extinction coefficient of 12,448 molar inverse molarity, inverse centimeters. So then calculate the units of activity in, I'll just say, mole per hour. So to do that, you'd have to know the volume of the reaction. I would give you that. And so this would be a matter of doing the calculation that we've done a handful of times, where we solve for A, and then when we say, okay, well, A is 65 molar, just putting a round number out there. Well, if I want to go moles per hour, well, this was done, let's say, measured per minute. Okay, so this would effectively, what I'm asking you to do with this is a dimensional analysis type of problem. So convert from molarity to moles. Well, you'd have to do that. You'd have to know the volume. Well, if it was a reaction that was 1 milliliter, it would be 0.001 liters. And that would get rid of the mole or the volume. And now we're down to moles per minute. Okay. Then the next part is converting minutes to hours. And well, dimensional analysis would be mole per minute, 60 minutes, 1 hour. There you go. So that's the sort of calculation that I would ask you. So I do not commit to memory the extinction coefficient for NADH. It's 6220, but do not worry about that. But I do want you to know wavelengths. I want you to know the significance of 340. And the significance of 340 is that we can measure NADH specifically, because NAD plus does not absorb at 340, NADH does. Okay. Does anyone have a question about any of that so far? I muted a couple of y'all, but I think you can unmute yourself, or you can add it to the chat. I'm looking at the chat right now. Okay, sounds good. So those are all like some of the parts of what I want you to be familiar with from this class. Then I also want you to recall enzyme kinetics and the different types of graphs associated with enzyme kinetics. So your Lineweaver-Burke or your Michaelis-Menten plots. What do those look like? What are the axes for those? Then from earlier on this semester, I want you to remember the methods that we use to try to purify lactate dehydrogenase. If you remember, when we were trying to purify lactate dehydrogenase, we used the salt. Does anyone remember the salt? That's right, ammonium sulfate. I know everyone was typing it, and sorry for, I just got impatient. Ammonium sulfate. So ammonium sulfate is a NH4 to SO4. So this is a salt that helps precipitate PPT proteins. EINS. And basically helps them get compacted and precipitated out of a solution. So it's kind of a purification method. If you remember the units that we used, it was 55 or, percent by saturation. So we made a saturated solution of it, we made it into a saturated solution of ammonium sulfate. Then we centrifuged it. So there's ammonium sulfate, we precipitated proteins. Then we tried affinity chromatography. And this affinity column that we used was known as Cibacron blue. We also used ion exchange chromatography. We used a DEAE diethyl amino ethyl column, and this is going to be a positively charged column. And this was a question that lots of people, or there are some people who had some confusion on. This column has a pKa of approximately, I think it's like 11.5. So what that means is that this molecule will be be positively charged until the pH, or the predominant form of this will be positively charged until the pH is greater than 11.5. So this works very effectively as an anion exchange column up until a pH of greater than 11.5. So if you had a protein that you had in a solution with a pH of 10, this would be, and it was a negatively charged protein, it's going to bind to this column. If you had a protein that was negatively charged at a pH of 13, this isn't the column for you. So we used those two types of chromatography. We used ammonium sulfate, and we were trying to purify lactate dehydrogenase. I would definitely know, like I would read through my old procedures and the background information. That's where I like to get a lot of questions from. So like goods buffers, for instance, I love to ask the question, what's a criteria of a goods buffer? Or what are the criteria that make a goods buffer? Those are some of the questions that I like to ask. Then like why was the Bradford technique so innovative? And the answer is because it was used visible light as opposed to UV light. And visible light is, in a sense, it's just cheaper than UV light. So I wanted to give you all like the overview of the exam. I have some things that I'm going to get caught up with grading this week, and I apologize for the delay on that. I think that I'll have everything graded before the end of this week, so you'll have a sense of where you are going into that final. And then in addition to this, when I'm writing the final, if there's something else that I did not mention here that I asked questions on, I will email everyone, or I'll post it as an announcement like, hey, don't forget this. But outside of that, is there anything that anyone has questions on? Okay, I always like to put a bonus question or two on the final, and so I expect that. But if nobody has any questions, I'm going to go ahead and let y'all go. And if you want to meet up with me about, preparing for this or preparing for your Bradford this week, just let me know, and I'd be glad to set aside time for that. But other than that, if I don't see you before Monday, I'll see you all on Monday, and I hope you have a great week.